What you're looking at here is a circuit board, and I think it looks a lot like a little miniature city. And in a lot of ways, it's very similar to a city. There's different things. These things kind of look like buildings here and here. And just like in a city, different buildings do different things. You have office buildings and you have restaurants, and they all kind of serve their different purposes. And in the same way, all of these, what are called components in a circuit board, do different things. Some of them act as one-way streets to send electricity in certain directions. Some of them speed up the electricity or slow down the electricity. And then you have all of these little pathways here that look like little roads, right? And these are very similar to roads because they are the areas where you get the transportation of the important part of the circuit board, which is the electricity that flows from one place to another. Now, last week we talked about static electricity. This week we're going to be talking about current electricity. Don't forget that red slides are where you have to take notes. You should have your notes handout ready to go. Don't forget to look for the owl and let me know where he is. And remember to fill in all of this stuff that you see here. So what's going on this circuit board here? Why do we have to have these little pathways here that allow electricity to flow? What's the difference between that part of the circuit board and this other part of the circuit board, say over here or over here where you don't have those pathways? Well, you may remember us talking about the idea of insulators and conductors. So insulators are the part that's kind of the outside part of the wire over here, and that's usually going to be made out of rubber, plastic, or really anything that's not metal. And so on the other hand, you have conductors, and conductors are things that are made out of metal and are able to conduct electricity. Well, what does that mean, conduct electricity? It means it allows the electricity to flow, or more specifically, we now know that electricity has to do with electrons. So more specifically, it allows electrons to flow through it. So that's kind of the idea of a circuit board. All these little pathways here are just little pathways of metal, and the other parts are not metal. So basically, like I said, these are kind of like little roadways here where the electrons can flow. They can't flow in this area because that area does not conduct electricity. So they just kind of stay on these pathways, and the pathways take them to the different components, the different little buildings in our city here where different things get done to the electricity, like slowing it down or amplifying the electricity, making more of it, things like that, redirecting it to different places, telling it to go in different directions, all that kind of stuff. And that's basically how computers, phones, all that kind of stuff, how they work. All those electronic gadgets have something like this in them that basically tell the electricity what to do and where to go. So I'm going to kind of change the analogy here a little bit. I've been talking about using the analogy of like a city for a circuit board, but really what I want you guys to think of is when you think of electricity, I want you to think of water, because the idea of electricity flowing through a wire is very similar in a lot of ways to water flowing through a hose. So this is going to kind of help you to picture it. Just picture it like water flowing through a hose when you think of electricity flowing through a wire. And here's an electrical wire right here, and if we were to take this electrical wire and look at it very closely with a very special microscope, this is what we would see. And this is a pretty amazing picture here because what we're seeing here is individual atoms of copper here. And one of the interesting things that you might notice is that they're all kind of in these nice, neat little rows here. That's kind of a cool thing. A lot of metals kind of line themselves up that way. Now, if we were to look even closer at this, what we would see is these nice, neat little rows of the nucleus of the atom and all of these little electrons kind of whizzing about here. And remember, one of the things about metals and conductors in general is that the reason why they're able to conduct electricity is because the electrons can kind of bounce around from one atom to another. Now, normally speaking, these guys are all kind of going in random directions, every which way. Some of them are going that way, some of them are going that way, and they all kind of bounce around. The electrons kind of bounce around from one atom to another. But in order to have electricity flow through this wire, and so this is kind of the wire right here, right? Like that is kind of like this, a little piece of this wire right here. And so in order to get them all flowing in one direction, well, we have to think about what we already know. What charge are electrons? They are negative, right? These are all negatively charged electrons. And then we have to think about what do we know about charges and what they do to each other. Well, opposites attract and like charges repel each other. So if we could put a negative charge over on this side maybe, and maybe a positive charge over on this side, well, the electrons would be attracted to the positive charge and they would be repelled from the negative charge, and they would all want to flow in the same direction, all in that way. And that's how we get a current of electricity to happen. So this is the idea of how something like a battery works, for example. A battery basically is just a sort of build up of something that has a negative charge on one side and a positive charge on the other side, and there's kind of a wall in between them where they can't really mix with each other. So if you put this wire, like this wire here, if you put this wire and connect it to this side of the battery and then loop around and connect it to this side of the battery over here, then the electrons in the wire, like these electrons that we've been talking about here and these electrons that we've been talking about here, these electrons will start to get pushed away from this side and they will start to be attracted to the positive side, and they will flow through the wire, and that is basically the idea of what we call current electricity. That's how it works. One of the things to take note of here is that if we cut this side off, if we take this side off of this side of the battery, then they really can't flow from one side to another. You need a complete, what's called a complete circuit, which is kind of like a circle, right? So it goes all the way around in a circuit from one side to the other, and you always have to have that kind of ability to flow from one side to the other. Again, just like water, if we cut off this side and block it off here, the water is not going to flow through the hose. It's going to get stuck and stop there, and it's not going to be able to flow. Same thing with electricity. It needs to be connected from one end to the other end without any breaks in between. So current basically is the idea of the rate of flow of electrons. Again, think of it like how much water is going through this hose. More water is like more electrons, more current. So to make that point, why don't you go ahead and draw some little electrons in your water there. Little electrons, just like the electrons that are going to go from the minus side because they are getting repelled by the negative charge side. They're going to go through this wire. They're going to go through these light bulbs, through the filament in the light bulbs. They're going to come out the other side, go through another light bulb, and all of these little electrons are what are going to make that wire in the light bulb light up. And then they're going to come around all the way to the other side and be attracted to the positive side and go back in this side of the battery. So there are basically two ways that we can make this happen. There are two ways that we can make electrons flow through a wire. And remember, as long as those electrons are moving in that wire, then you have electricity. So first of all, we have direct current, or what's called DC current. And this is a flow of electrons in one direction, which is kind of what we've been talking about so far, that way. And we have alternating current, or AC, and you've probably heard of these things before. So, two main kinds, and what do you think I'm going to have here? Of course, AC/DC. So, DC current is a flow of charge always in one direction, and I want you guys to associate this with batteries. As I told you before, batteries are basically a bunch of negative charge on one side which pushes the electrons away from it, and a positive charge on the other side which then pulls those electrons towards it, and you complete that circuit. And think about this, batteries run out of juice eventually. Batteries die, right? Well, what does that mean when batteries die? Well, if you think about it, all of these little electrons over here are being pushed in the direction of the through the wire, and they're going through the wire and they're ending up on this side. So what's going to happen? Well, the negative charge on this side of the battery is getting depleted. It's running out of electrons, and the electrons are going over to this positive side. So this is going to build up a bunch of electrons. So you're running out of your negative charge on the negative side, and you're kind of getting rid of the positive charge by putting all these negative electrons onto the positive side. So as you do that, the negativeness of the negative side is going to get less and less, and the positiveness of the positive side is going to get less and less, and that's basically your battery running out. To recharge batteries, like the battery in your phone, all you have to do is send those electrons going back in the other direction. That takes some energy to do that. We have to push them back in the other direction, and so that's why you have to plug your phone in and get some electricity to make those electrons go back through here and go back to the other side and build up your electric charge here again, so that your battery is now charged again. And notice we even use that word charged because we are creating an electrical charge, an imbalance in a charge in the battery. When we recharge it, we are putting all those electrons back on one side and taking them away from the other side, which makes one side more negative and one side more positive, and that's the thing that pushes the electrons through the wire. So these guys all go, remember, in one direction, but yeah, no, not that one direction. Thank you. All right, so the other kind is called AC, or alternating current. This is a flow of charge back and forth, changing its direction many times per second. I want you guys to associate this with the plugs in your house. These are the things that you plug in, like the toaster and the refrigerator and the TV and stuff like that. Things that are plugged into the wall, that uses alternating current. That's what comes out of the outlet in your wall. You can kind of think of it like this. This is like sort of a graph of alternating current. It just flips between the negative charge and the positive charge, which basically makes it so the little electrons keep going this way and then that way. They keep going back and forth because when you have a positive charge, the electrons get pulled towards it, and when you have the negative charge, the electrons get pushed away from it. So they're constantly kind of jiggling back and forth and back and forth and back and forth. And again, that's movement of electrons, so that counts as electricity. Now, why do we use alternating current, which seems a little bit more complicated? Why do we use that for all of our power lines and our outlets and stuff like that? Well, there's a couple main advantages of this. First of all, the voltage can be changed. You can raise and lower the voltage to whatever you want, and it's more efficient over long distances. You can see in this picture that electricity has to travel a really, really long distance over these wires from the electrical power plant to your house and all the other buildings. So DC current kind of tends to lose some of its energy as it goes through here. So AC works a little bit better for going over long distances. All right, now we need to talk about properties of current electricity, the different things we can change about it. Remember when we talked about properties of waves, we talked about you could change the amplitude or like the height of the wave, or we could change the length of the wave, things like that. So we need to talk about properties of current electricity. So the first one is called the ampere, or you may have heard of it as called amps. This is a measure of how much current moves through a wire in 1 second. So again, think of it like water going through a hose. Less amps is like less water. It's literally less electrons moving through that wire. More amps, well, that's like more water, more electrons moving through the wire. And just like with a hose, a smaller hose lets less water through and a bigger hose lets more water through. Well, in electricity, smaller wires let less amps through and bigger wires let more amps through. All right, voltage. This is our next one. Voltage is sort of the force that pushes the electricity. It's like how strong that battery is, how hard it's pushing and pulling on those electrons. You can think of it like the steepness of a hill or something like that. This is kind of a potential energy. It's how much negative charge you have on one side and how much positive charge you have on the other side. So it's how strongly those electrons are being forced through that wire. Generally speaking, the outlet voltage in your house is anywhere between 120 volts and 240 volts. The regular outlets that you see in your house, like this one, are 120 volts because we say that the voltage has been stepped down to that. They reduce the voltage before it comes out of these outlets to 120 volts, and that's what most things use. But you do have some things in your house that use more than that, 240 volts. Things like large appliances, like your dishwasher or your washer and dryer for your laundry and stuff like that. You may have seen an outlet in your house that looks like this. Well, that's the 240 volts. I want to kind of make sure at this point that you guys understand that both of these are extremely dangerous. You should not mess around with this. This really could be very dangerous. And when I say very dangerous, basically what I mean is that your body works on electrical signals. And so if you get zapped with one of these, what could potentially happen is that your heart could actually get too much of a signal, and you could kind of overload your heart and have a heart attack if you mess with this stuff. So very dangerous stuff. Do not ever mess with this stuff. All right, so voltage was kind of the idea of how hard of a push you have on these electrons, and amperage was kind of the idea of how much electricity is flowing through there. We've been kind of talking about the amount of electricity flowing through. Well, you guys probably know what it means to resist something. It means to kind of go against it. So that's what it means in electricity. Resistance is opposing the flow of electricity. It is slowing down the force of electricity. So again, going with our water analogy, it's kind of like putting a dam in a river. It's very similar to that. It's something that slows down the flow of electricity, just like a dam slows down the flow of water. So this turns electricity into light and heat. That's what happens. That's basically how things like light bulbs work. And the unit that we use for this is called the ohm. This is the Greek symbol ohm, so that's the symbol for it. And again, it's kind of like putting a dam in your circuitry, or you could think about it like this. You could also kind of think about it like friction for electrons, and this is a good way of thinking about this. By the way, what type of image is this? See if you remember from earlier on. Think about the electromagnetic spectrum. It's right next to red. Oh yeah, that's right, infrared. Very nice, good job. So what kind of things are resistors? Well, these kind of things are resistors. To be honest, pretty much anything that uses electricity is a resistor. Remember, it creates light and heat. So the light that's coming out of this clock, created by resistors. The heat for the toaster, created by resistors. The light and heat that comes out of the light bulb, yeah, that little guy right there, resistor. The thing on top of your stove that makes it get hot, resistors. All of those things are resistors. Now, sometimes resistors are things that you don't see that are sort of inside the circuit board, and those can just be used specifically to slow down the electricity, but a lot of times we use resistors to do something for us. We use it to create light and heat and things like that, because remember, it's basically friction for electrons, and remember, friction creates heat. Now, remember the idea also that conductors, like those guys, have a low amount of resistance, and insulators, like those guys there, they have a high amount of resistance. That's basically the idea of what makes a conductor and what makes an insulator an insulator. Insulators have lots of resistance. They don't let the electricity flow through them. Conductors have very little resistance. They let the electricity flow through them pretty quickly. Okay, so this is Ohm's law right here. This is the idea. Here's another formula for you. Voltage equals current times resistance, or V equals I times R. That's a formula that you'll need to know. Let's try a couple of these out. So remember I said that your household electric outlet is 120 volts. So if you put something into that, if you plug something into that that's 60 amps, well, how many ohms would that be? We have to think 60 times what is 120? Well, 60 times 2 is 120, so that would be the answer to that one. Let's try one more. How about a 12-volt battery? If you hook up something that has 3 ohms of resistance to a 12-volt battery, How many amps are you going to get out of it? Well, 3 times what is 12? Let's see, 3, 6, 9, 12. You couldn't see me there, but I was just holding up 4 fingers, so that must be 4. Next thing I want to get to is the idea of power, and you might remember this slide from a previous homework assignment. We've talked about power before, and so power in the case of work and force and things like that was the amount of work that you did in a certain amount of time. Well, that's kind of the same idea in electricity. Power is the rate at which electrical energy is turned into other forms of energy. In other words, it's how much light you get out of something in a certain amount of time. And you might have heard of this in light bulbs, right? Because you've heard of the wattage of light bulbs, and that's a good way of thinking about this, right? 25-watt light bulbs are very dim. They put out a very small amount of light in a certain amount of time. So if you sat there and looked at a 25-watt light bulb and a 100-watt light bulb and kind of saw how much light you were collecting from those guys in, let's say, a minute, then you would find that you get much more light in much more light in 1 minute from a 100-watt light bulb than a 20-watt light bulb. So one more formula for you here: power equals voltage times current. Remember, these are all things we've talked about voltage and we've talked about current before. So power is sort of a combination of those two things. So more power, more watts is more light, more speed, more volume. So think of those kind of things. You just get more from your electricity if you have more power. All right, so those are the basic things you need to know about current electricity. We learned that current is the rate of flow of electrons. We learned that there are 2 types of current electricity. There is DC, which is only one way, and we need to associate that with the energy that we get from batteries. There is AC, and that is back and forth, and that is associated with household outlets, the things that we plug into the wall. We have a few different properties of current electricity. That is the ampere, voltage, resistance, and power. And we have a couple different formulas that we need to know this time around. Voltage equals current times resistance, or V equals I times R, and power equals voltage times current, or P equals V times I. We'll be doing a whole bunch of stuff with electricity in class, including making some circuits and making some light bulbs light up and things like that, and I will see you then.